This is Unit 2, Day 1. We're going to talk about average rate of change and introduce the idea of instantaneous rate of change. So first of all, it should be review the idea of average rate of change. Average rate of change is simply the slope of a line that connects 2 points on a function. Average rate of change, you guys can think of it as y2 minus y1 over x2 minus x1 on a graph. Now we are going to be focusing on graphs that aren't linear. We'll be talking about from one point to another point on the graph, what is the slope of the line between those 2 points? The slope of the line between those 2 points is called the average rate of change. If this is x2, y2, and this point here is x1, y1, then we know the slope of that line is y2 minus y1 over x2 minus x1. But using function notation, a better way to describe this point would be x1 comma f of x1. And using function notation, this is x2 comma f of x2. So y2 minus y1 can really be thought of as f of x2 minus f of x1. Second y minus first y. And the denominator is still the change in the x's, x2 minus x1. In general, f of b minus f of a over b minus a, average rate of change between 2 points on a function. Now, when we draw this line that intersects our function at two distinct points, this line is called a secant line. It cuts your graph at 2 points. Average rate of change of the function is the slope of that secant line. Now we're going to take this idea of average rate of change and use it to build an understanding of instantaneous rate of change in the next section. We are going to be using Excel to help us with some of our calculations. So for example, if we have Excel open and I have an X value here in A1 and its associated Y value in cell B1, and then a second point, I have this X value in A2 and its associated Y value in B2, then we know the slope of the line between them, the average rate of change of the secant line. To calculate that, we need to take this y2 minus y1. So that would be cell B2 minus cell B1. And we need to divide it by x2 minus x1. So that's cell A2 minus A1. Now we got to be very careful with parentheses when we actually type that in Excel. We need parentheses around the entire numerator and we need parentheses around the entire denominator. So we're going to watch out for that common error. So in this problem, we've been given an exponential function that has a starting value, a y-intercept, 323,000. We see that it's an exponential function that's increasing at a rate of 6% every year. It tells us that we're inputting the number of years since 2000 and it's outputting the number of AIDS cases. We've been asked to find the average rate of change of this function from 2001 to 2015. So recall, average rate of change is going to be our change in y over change in x on this function between those 2 points. So when they say 2001 to 2015, we're talking about x equals 1 up to x equals 15. So we're going to do f of 15 minus f of 1 over 15 minus 1. So y2 minus y1 over x2 minus x1. So I need to find the y value when x equals 15. So I'm going to go to my function. I'm going to plug in 15. I'm also going to plug in 1, and I'm going to find the y values. So I've already done this over here in Excel. Here in Excel, I've plugged in the function 323,000 times 1.06 to the x, and I'm going to come over here and plug in 1 and 15 for the x's. So I see here that the X is 15, maps to 774,088 approximately as the Y. And when you plug in 1, you get about 342,380. We can use Excel to help us calculate that difference. So when I subtract them, it'll equal this cell minus this cell. I get 431,708.2964 all over 14. And so again, in Excel, I can have it calculate that difference, that y2 minus y1 divided by 14. So I'm going to say it's approximately 30,836.3. Notice I could have done that all in one step in Excel. I could have it calculate in parentheses y2 minus y1 divided by, in parentheses, x2 minus x1. And we get the same. So you don't have to do it in multiple steps. Excel can do it all in one step. We also, of course, want to interpret the meaning of this number. This is a rate of change. It is a slope. So when we're interpreting a rate of change, we're going to have units in the numerator and units in the denominator. The numerator here is number of AIDS cases, how much it's changed. The denominator is number of years, how much that has changed. So when I get this answer, 30,836.3, I'm first going to write it as a fraction. I'm going to put it over 1. And I notice the numerator is the increase in AIDS cases, and the denominator is the increase in years. So we're saying as you go over 1 year, you go up 30,836.3 AIDS cases on average. So from 2001 to 2015, AIDS cases increased 30,836.3 cases per year, and you should include the words on average because it isn't a linear function. It does not have a constant rate of change of 30,836.3 per year. It's only doing that on average. So on a graph, what we were doing there to sketch out what we just showed, what we just calculated graphically, here is that increasing exponential function f of x. We went from year 1, when there were 342,380 cases, up to year 15, when there were approximately 774,088 cases. And when we performed our average rate of change calculation, we were imagining this secant line that intersects the function at those 2 points, and we said the secant line's slope is 30,836.3. It increases 30,836.3 per year. Over a year, up 30,836. Over a year, up 30,836. Over and over and over the course of the 14 years. In example 2, the amount of surcharge for non-account holders at an ATM can be modeled with this exponential function. So here is the starting amount, and we see it's again increasing 8.1% per year. It says we're inputting number of years since 1995, and it's outputting the actual surcharge, so that would be in dollars. Identify the average rate of change from 0 to 3, and identify the average rate of change from 9 to 12. This time I'm going to do this with like the short method in Excel. Calculate it pretty quickly. So in Excel, I have created an input-output table, the formula 0.72 times 1.081 to the x, and I have input these values 0, 3, 9, and 12, which were the values of interest in the problem. I'm going to add a column C on the right where I'm going to calculate the average rate of change. Now here in cell C3, I'm going to calculate the rate of change from average rate of change from 0 to 3 in this cell. You'll notice I skipped this very first row. I'm going to start this calculation here. All right, to calculate the average rate of change from 0 to 3, it's y2 minus y1 over x2 minus x1. We're going to make sure to use parentheses around the numerator and denominator. So here is y2 minus y1 in parentheses divided by, in parentheses, x2 minus x1. So this will calculate the average rate of change from 0 to 3. Turns out it is 0.06. We're doing s of 3 minus s of 0 over 3 minus 0. I performed the calculation in Excel, and I got about 0.06. The units in the numerator, this is dollars of increase in the surcharge, and in the denominator, this was years increase. So my answer still has dollars of increase in the numerator divided by years of increase. Remember, you can always write a number over 1, so the denominator here can be 1. I'll do it again for the time period from 9 to 12. Again, I'm going to put my cursor down here at the row where that interval ends at x equals 12 and do the calculation. So y2 minus y1 in parentheses divided by x2 minus x1 in parentheses. And this time I get about 0.13. So s of 12 minus s of 9 over 12 minus 9 came out to about 0.13. So that's dollars of increase over years. So this is telling me the average amount of increase per year on each time period. So t equals 0 to t equals 3 is 1995 to 1998. So from 1995 to 1998, the surcharge increased 6 cents per year on average. Again, you've got to use the words on average because this is an exponential function. It does not have a constant rate of change. This is just what's happening on average per year. From 2004 to 2007, that's 9 to t equals 9 to t equals 12, the surcharge increased 13 cents a year on average. So how is the rate of change changing? Well, this is an exponential function. It is concave up. We went from 0 to 3, and we had this slope of this secant line, 0.06. When we cut over here to 9 to 12, it was steeper. The secant line was steeper because the graph is getting steeper. So over here from 9 to 12, the slope of our secant line was 0.13. So we can say that the rate, that is the slope, the rate is increasing. I could say the function is increasing at an increasing rate. And this word rate, we're thinking slope. The slope is increasing. It was 0.06, then it increased to 0.13. The rate is increasing.